are you going to time yourself? Okay. He's got a time.
Thank you. So I'm going to talk about the quantifying fitness in clonal hematopoiesis. I'm using a Logistic Moran modeling in evolution, dynamics, and therapy response. Thinking of evolution, we usually consider as a million of years, but sometimes this is not the case. For example, if you mutated the stem cells in your bone marrow, not mine, it starts to grow faster than the rest of them, and then they expand their territory. A phenomena that we call it clonal hematopoiesis, or CH. So first of all, I want to actually say the importance of CH, and then I want to talk about the fitness inference, the model, the evolution inference, and then the therapy bottleneck, and how to validate our model. So what is CHIP, clonal hematopoiesis of indeterminate potential? It's very hard for me as a non-native English speaker to pronounce it. So consider as CH. So if one of the mutated cells grow and their VAF or the frequency is more than 2%, we call it CHIP. This is literally bad news, you know, that this happens for everyone due to the age. If they don't do any other wrong things like this, smoking or sunset, too much UV exposure or other things, they will happen because of the age. Why does CHs matter? Because it could be a precursor of so many diseases, like Alzheimer even, like cancer, heart failure. But what we are interested is more about the cancer. CH is more prevalent in people with cancer, especially later in life when they get older. Okay, I hope that you convinced that CH is important, but like, why do some clones expand while others do not? I don't know the answer. That's why we use mathematical model to get some inference. In terms of CH, for me, it's very hard to keep standing behind the microphone. I usually get used to walking the, yeah. Can you hear me? Oh, thank you so much. It's very convenient. Okay, if you want to actually think about the CH, in our hierarchical models, in our bone marrow, we have HSC stem cells, and then they're differentiate to different types of immune cells or other responsible cells for our body. Sometimes the stem cells starts to increase their proliferation rate. Some mutations happen. This mutation can be extrinsic or intrinsic mutation. And then the differentiation block happen, and all these side effects could occur, like the cytopenia or immature cells or inflammation. So this skewness or this imbalance of proliferation in stemness and the differentiation makes the CH. CH makes this imbalance. So this imbalance is another bad news for us. So how we can study the CH dynamics with the math model? We use the VAF concept, which is the variant allele frequency. So literally, we count how many mutated cells happen in our stemness population. So we can think of VAF longitudinally. So we sequence the blood sample in time and calculate the VAF from time to time. And if the VAF increases, then for that mutation, there is a positive fitness. If the VAF decreases, we can consider as a negative selection. So for this one, we need to sequence the blood samples in time. Sometimes, for example, at some point of the time, we sequence a sample of blood and look at the distribution of the VAF. Based on the distribution of the VAF, we can actually infer whether the stem pool size was expanding or it is stable. If this is actually the distribution of the VAF is not F-1 in the hematopoiesis state or in the adulthood, then something is going on, like there might be some mutated cells there.
C'est limité en fait. Quoi? C'est limité.
Déjà limité.
Yes, yes. We can hear you. Yeah, do you have any comment?
Could people online please mute themselves? Sorry, I'm going to do it.
Sure.
Where is it? Sorry, I don't know how to do that easily here. Let's just hope they don't open their mouth again.
Okay, so from one single time point, I said like we can actually have some inference. I want to actually mention the Krieger paper, which was very nice one, that he proved that like during the developmental state of our life, which before birth, if any even weak selection happens, then those weak selection does matter later in our life, which was very significant, which was very interesting. Okay, so we use VAF to study the dynamics of the mutations. And then how mathematical models can be helpful for us. So what I want to present is a stochastic and deterministic model, like a Moran process, and for the deterministic one, the logistic and exponential model. So what is the usefulness of those models? They can separate the stochastic drift from the true selection if we use the Moran process. We can estimate the clonal fitness. The fitness concept is the most important concept in CH because we can actually infer if the mutated is expanding or not. And if the mutation expanding, there could be some precursor disease happen afterwards. And we can quantify the trop impact. It is very astonishing because sometimes we go and get some chemotherapy, we are happy, oh, the remission happens. But in some cases, the patient come back with another types of cancer or with the relapse. So we call it as so there is a TMN for those patients. So this TMN is a sign for us when we do the model of the CH in the coronary hematopoiesis to see if, especially after the bottleneck effect or after the therapy. So first, I want to present the deterministic approach. For the deterministic approach, we can use the logistic versus exponential model. Very easy peasy. So something actually rises here. If the VAF is high enough or in the course of time, the logistic goes to the infinite, which doesn't make sense biologically. We don't have that big VAF for any mutation. So eventually we got saturated. That's why we believe the logistic equation for the deterministic approach is a better approach to infer the fitness. So that's why I use a Bolton data set and then fit these famous mutations in this data set with the logistic equation and the exponential one that they did. And I observed that the exponential model kind of underestimate the growth rate of the VAF. So the fitness is different if you use either of these deterministic approach. For the stochastic approach, we have the Moran process, like I can hear you if you have something to present.
Yeah, I'll try.
Okay. So what we had a really nice presentation yesterday that for the Moran process and how they infer the fitness. And one of the advantage of the Moran process is we can actually compute the fixation probability at the time of fixation or extinction probability analytically. So this is simple Moran process I put here. We choose one of the cells randomly to divide. There should be another cells to die and then replace it. So after one time process, there will be no change of white type cell proliferation or the mutated proliferation. This is an example of one mutation there with the constant Moran process. In case of we want to compare the logistic and Moran process, another advantage of using logistic equation for our deterministic model, the logistic one can mimic the Moran process more accurately because of the reason the logistic gets saturated sometime later. But if the fitness is low, then we have more likely to have an extinction. That's why the logistic deterministic model is very different from the Moran process fixation versus the high fitness. How we can use we can infer the evolution inference using a Moran process. There could be symmetric self-renewal, asymmetric division. If there is a mutation, the self-symmetric renewal increase significantly. So I have some examples of how to use the Moran process. If we have a neutral constant HSC or neutral evolution, no selective or no mutated or selective advantage fitness in our population. We have a constant population, we have a neutral evolution of phylogenetic tree, and the Muller plot shows multiple coexistence of clone fluctuate together. On this paper, based on the data, they observed the symmetry tree when we don't have any mutation, compared to if there is a selective mutation in our simulation, then we can observe the effect of this mutation in our phylogenetic tree that makes our phylogenetic tree asymmetry, and we see on the Muller plot. Again, on this Mitchell paper, they had a patient with the mutation, and this asymmetry is obvious on their tree as well. If there is a trophy or bottleneck effect, so for example, we get the trophy. Sometimes the trophy makes the mutation or mutated cells expand faster because the population size decreases. In this paper, we observed, we had the chemotherapy on the breast cancer cohort on 171 patients, and we observed, compared to the hormone therapy, the allelic population decreases more significantly, or 8 times more reduction in the chemotherapy. And if there is a positive selection on those patients, we observe some of the mutation expanded faster after the therapy. This paper is under review, and you can find it on the medRxiv. Speaking of the validation, so I said we can actually look at one-time VAF of our blood samples. Let's see on the first row, there is a growth before life that I use the Moran process to simulate. And so cells start to grow in the neutral assumption. And on the second row, as I showed you before, there is a homeostasis or adulthood. We can actually look at one blood samples. So this is output of this simulation. The distribution of the VAF is following the slope of minus negative in the adulthood, or following the -2 slope around -2 in the developmental state. And the reason is because in the adulthood, we have more mutation in the course of age. When we have more mutation, then we have more high VAFs in general. That's why the slope is minus negative and the other one is -2. Thank you so much for your attention and for organizing the conference, and my lab members in Edith Lab. Thank you.
Any questions? Yeah. Yeah, thanks. Very interesting. I have a question about your stuff about logistic. Were you fitting a logistic to the mutant dynamics?
Yes. I fitted the logistic equation to the muted dynamics to see like the growth, because if you have a muted dynamics, we have some fitness for that muted dynamic. Actually have the S value on our logistic equation.
And did that logistic include the wild types as well, or only the mutants?
No. I use logistic to fit the mutant dynamics on the Bolton data set here.
Right, I see. But they do compete with the wild
Yes.
type, so
Yes.
it may be a better approach to kind of like in your Moran process, you have them both together, right? It'd be interesting to compare if you do that with the logistic as well.
Yeah, you are right. But like in Moran process, we usually use the fitness as 1 plus S, which S is the growth rate of the mutant.
Right.
Yeah, like for the wild type in the Moran process, we consider S as 0. So the our fitness of our wild type in the Moran process is 1.
Yeah, you could scale it in the
Yes.
ODEs as well, I think, and have 1 plus
Yes.
S times the replication.
Yes.
Yeah. Okay.
Yes.
Yeah. Nice.
Yeah. Thank you.
Any other questions? Okay, thank you. Thanks, Sandy. Okay, next.